Welcome to Current Electricity Part 2, where we look at two things. We look at various ways that we measure elements of a circuit. And the second thing we want to look at is a brief introduction to different ways we can wire a circuit. The first thing I want to talk about is this device. When we measure electrical current, what we're really measuring is the rate at which the electrons are flowing past a particular point in the circuit. And the unit that we use to represent this is something called the ampere, or the amp, or capital A. And just like the metric system, we can also have tinier units called milliamps, and the difference between 1 amp and a milliamp is 1,000. So if I have 2 A's, 2 amps, what would that be in milliamps? That would be 2,000 milliamps. So here's our ammeter. Believe it or not, when we're measuring weaker electrical current, we don't use an ammeter, we use something called a galvanometer. And I know this is a galvanometer because I can see the units of milliamps. However, when I look at this meter, it's measured in amps, and so I would call it an ammeter. So two different names for the devices: ammeter for stronger current and galvanometer for weaker current, which is in milliamps. When we hook up a galvanometer, which would be a circle with a G, or an ammeter, it's important that it is connected as part of the circuit. Now we call that hooked up in series, which I'll show you a little more on in a minute. So its electrons have to flow straight through it, like in this circuit diagram. Electrical current is usually what is most harmful in organisms, and we usually have a saying that says current kills. And so how much? Well, let's look at these figures. So if your body was subjected to somewhere between 1 and 10 milliamps, you would feel a mild sensation. However, as the current gets stronger, when you get up to 30 milliamps, you're going to have paralysis. And when you get up to 250 milliamps, your heart's going to basically fibrillate, which isn't good. And by 4 amps, your heart is going to paralyze. So, yeah, anything in this zone is almost deadly. So here's a good thing. It says currents between 100 and 200 milliamps are considered lethal for humans. So what is that? Well, let's convert that to amps. So 0.1 amps. So this threshold. So how many amps come out of a light socket? 15, which is why you shouldn't stick your finger in a light socket. And this is an electric eel, and it gives off 1 amp, which is also lethal. Let's talk about voltage now. Voltage has to do with something called the electrical potential. And so what happens is we have a power source that helps push or drive the electrons along the wire. Now, the device that has the pressure to push the electrons, we call that the voltage. The higher the voltage, the more energy, the stronger the push. And we use voltmeters to measure voltage. There's no such thing as a a smaller meter like in current, so there's no device that we would give a different name if it was measuring weaker current. Uh, when we hook up a voltmeter, it has to be attached kind of outside the current. So we would, if we wanted to measure the voltage here, we would put one wire, just touch it along there, and then we'd put the meter here, and then we'd connect the other wire right there to measure the potential difference or the amount of energy or how much push it can provide. Let's say we want it between here and here, then we would hook the wire there, and we call this hooking up in parallel. And voltmeters have to be hooked up in parallel, whereas galvanometers and ammeters have to be hooked up as part of the circuit or in series. Let's talk about water as an analogy for what's happening with circuits. So far we've talked about voltage, which relates to the power source and how much can be pushed. We've talked about the flow of electrons, and that's current. The third thing that's part of a circuit is devices that are used to slow down the flow of the electrons, and we call that resistance. A resistor can be a lamp or anything that helps to slow down electron flow. Lamps and bulbs are good examples. So let's look at an analogy. If we take this picture with the dam and we look at water behind the dam and we talk about a hole that we've made through the dam to allow the water to spurt out. Now, if the water is only this high in the dam, that's not a lot of pressure providing. So we would say that would be like a small cell, 1.5 volts. However, if we increase the amount of water, that's way more pressure pushing out of the hole, then we've upped the size to maybe a 6-volt battery. And if we really fill up the dam, now the water flowing out of here is super strong, which means this is a bigger voltage battery. So voltage is again related to how strong it can push along those electrons. And so the dam analogy is a good way to think of how that works. The other thing I want to show you is the two different ways that we can hook up things in a circuit. When everything is hooked along a line and there are no alternate paths along the wire, but electrons only have one way to go, and that is through this path, we say that it is a series circuit. And if something is stopping the flow of electrons along a series circuit, then nothing will work. The circuit is open. So for example, let's say this bulb, the filament in this bulb burns out. It's done. Electrons go this way, put the switch down, it goes through the switch, it goes up through here, but as soon as it gets here, the circuit is open. So that would mean none of these bulbs would work, because remember, in a circuit, electrons have to come back to the original source. They need a pathway. So the downfall to series circuits is that with just one path, just a one-lane highway, if something goes wrong in the circuit, like a bulb goes out, then your circuit won't work anymore. So to summarize, a single pathway, the current will be the same everywhere along the circuit. Each device provides resistance, and the total resistance is the sum of all the devices. However, let's look at a parallel circuit. In a parallel circuit, we have one path here, but as soon as we get to this junction, electrons can choose different paths depending on what's happening. They can go this way, or they can go this way through the circuit. and so on. And so this picture really shows you the benefit of a parallel circuit. Electron flow, they get to the junction. If this switch is open, no problem. Electrons can go here and that light will go on, and they can follow this path and that light will go on. Or if this bulb burnt out, no problem. Then electrons could still flow up this and we'd at least have one light going. Now, unlike parallel circuits, the resistance, these bulbs, which act to slow down the electrons, work independently of each other along here. And we'll get more into how we calculate that later on. So in summary, each device connects to the voltage source. The voltage is the same across. The current from the sources isn't summed up. And we'll find out mathematically using Kirchhoff's law how we will find that. So let's look at this. If this was our circuit, it would be in series. What would happen is all these, ohm is how we calculate resistance. Okay, that's our unit for resistance. And so electrons flow through here. The more we add resistors, the slower all the electrons will flow along the highway, because the highway is being backed up. In a one-way highway, as soon as you have an issue, everybody is slowed down along the highway. Whereas in a parallel circuit, it depends on what's happening in the highway. For example, here's a path that electrons can travel here, and that's a 30 ohm resistor. They're going to, because that's a higher resistor, they're going to be going slower. If electrons go through this loop, that's a 20 ohm resistor, they'll have a little quicker speed, and this loop would have even faster speed because it's a lower size resistor. So different pathways, different speeds along the highway, etc. So that's my brief introduction to electrical circuits and how they work.